Welcome back. So last time we did the short-time existence of Ricci flow based on a general existence theorem of Richard Hamilton for nonlinear equations with an integrability condition, and we saw that the Ricci flow is essentially sort of a model case for that theorem, where the integrability condition comes from the second contracted Bianchi identity. It's a powerful theorem. I will show you at the end of this lecture how to apply it, say, in mean curvature flow. But it's also useful to have a more direct approach. And this more direct approach is due to Denis de Turck, and it is based on trying to get rid of the diffeomorphism freedom by finding an explicit diffeomorphism, a specific diffeomorphism to use in order to break the degeneracy in the symbol. So here's the approach of Denis de Turck. Use the flow along an explicit diffeomorphism to change Ricci flow to an equivalent flow which is parabolic in the sense of the first main theorem. Of the last lecture. That's the goal. So the question is what vector field to choose. So which vector field should we choose to change the flow? Now, in many papers and presentations, this just falls out of the sky, that this works. But with what we have just done, we can make an educated guess what we should do, what is a particularly good choice. And we had seen we know that the degeneracy of the symbol occurs in direction of the diffeomorphisms, occurs in diffeo direction, and on the null space on the, no, not on the null, vertical to the null space, of the second Bianchi. So this suggests that we should take something which you get out of the second Bianchi operator, out of this operator J, then apply it to a suitable variation. So for a variation Hik, we could therefore set Vk to be a vector field GJL times, and then we just take the gradient of JHKL minus 1/2, the gradient K of HJL. So if we have such a variation field, HIK, then we can form this vector field. We should somehow, if this is not zero, this is sort of the bad direction somehow that we should subtract. Now to recognize this more clearly what this is, let's be more fair here with the indices, right? There's a symmetry in J and L, so we can write this in a more fair way as 1/2 GJL times gradient J HKL plus gradient L HKJ minus gradient K HJL. Right, that's just an observation. And now you say, and I know this looks like the Christoffel symbols with H in here. In other words, well, H is a variation. So this is exactly the variation of the Christoffel symbols that you get in direction H. So we can write this here as the variation of the Christoffel symbols at the metric G applied to the let me see how to write this. This would be gamma I j k times G Ji. But it is coming from the differentiation of the Christoffel symbol in direction H. So now this is sort of the vector field somehow that at the infinitesimal level we should choose something like this. After all, right, this is happening after the linearization. And after the linearization, this seems to be the right direction to take this thing here. Now, how do we create an actual vector field before the linearization that leads to this term when we linearize? Well, we have to replace somehow this derivative with a difference quotient. So here's the definition of a vector field. This is just a variation vector, but now we define a vector field and we take Wk on the manifold along Ricci flow. We take G upper ij of gamma k ij minus gamma bar k ij, where gamma bar is the Levi-Civita connection of some background metric. And in the choice of the background metric, you are free. For example, you could just take the Levi-Civita connection of your initial metric at time 0, and then along the flow that you're looking for, you define this vector field, and notice that the difference of two connections is a tensor, so taking the trace here gives a true vector field, independent of coordinate system, really transforms like a vector field. And then we know that the Lie derivative of the metric along this vector field produces an extra term. Let's do that computation. we have a vector field, and the hope is that if we change Ricci flow by diffeomorphism in the direction of this vector field, that the bad terms in the symbol will disappear. So then look at the new evolution equation system. And this is the idea of the Turk. We take ddt of gij tilde of t equals minus 2 times the Ricci tensor of the tilde metric at t and at each point, plus the Lie derivative in direction w of g tilde ij. And as we know, this means that we solve minus 2 r tilde ij t plus gradient I wj at t plus gradient j wi at t. Now, we have already done the linearization, what happens when we compute the symbol of a variation of the metric in direction of such a diffeomorphism. And remember, it was exactly cancelling out the zeta squared term, the good term that we got in here. We had one good term and one bad term, and the variation of such term here of the metric introduced exactly the bad terms. So now you do the computation, and I leave this to you, because essentially we've done it. You compute if this is now your q tilde ij of g tilde of t, when you compute that sigma of dq tilde of g tilde applied to some zeta direction times a variation hik, the bad terms exactly cancel out and we end up. In other words, this flow is now uniformly, is now parabolic in the classical sense. So this Ricci de Turk flow is parabolic in the classical sense. Meaning, we can apply the theorem that we had stated, that you can find in Eidelmann's book, for example. So we get a smooth solution for this changed flow on a short time interval. So we get the corollary for any smooth initial data. Initial metric G0, there is a smooth, unique solution on some short time interval to Ricci de Turk flow. with these initial data. Okay? Okay, so we can solve this flow, and now, since this term here is just the Lie derivative along this vector field W, now the idea is to take the time-dependent diffeomorphism associated with the vector field W to just pull back in the other direction and get a solution of Ricci flow. So now, in this smooth solution, in particular, of course, we have the smooth vector field. So note that. Then on 0t cross Mn, W of t is a smooth time-dependent vector field. So we can look at the families of the diffeomorphisms. So let P of t be the family of diffeos, just like in the first lecture where we talked about Ricci solitons, such that d dt of phi of t is equal to W of phi of, at each point, P is W to phi of t of P at t. So, okay? With initial data to be the identity matrix. And we take a minus sign because we want to reverse now what we have done in changing the Ricci flow. And then you just check, exercise, check that the metric G of t, which is just the pullback of phi star of the metric G tilde of t, satisfies the original Ricci flow. Okay? And of course, because it's the identity here, we then have G of 0 as G. So we solved our original problem. You need an extra argument in order to prove uniqueness. This proves the existence part of a smooth solution to Ricci flow. If you want to prove uniqueness, you either have to appeal to the other theorem of Richard Hamilton, or you have to use the uniqueness of the Ricci-de-Turck flow and prove one more thing, namely prove that the vector field W that you're creating this way is also unique. So you have to write down the evolution equation for W, and then you get for W an evolution equation which looks again like a heat equation, and from this you can conclude by say, Grunwald type argument that since the two vector fields were the same at the beginning, they have to remain the same, and that gives you the uniqueness also in this Ricci-de-Turck approach. Okay, this completes the proof of short-time existence for Ricci flow, but I think it is worthwhile pointing out how the idea of both de Turck and Richard Hamilton relate to mean curvature flow, because there's a striking analogy between what is happening in Ricci flow and what is happening in mean curvature flow. now the analogous result of the mean curvature flow. So remember, here we had given some initial submanifold and let's take a hypersurface for simplicity, but all I say is exactly the same for any codimension, and actually you could go into any Riemannian manifold. It just makes the formula a little bit longer, the linearizations and the arguments will be exactly the same. So let's just assume we are in Euclidean space with the standard metric and then want to solve ddt of f is equal to the mean curvature vector, and the mean curvature vector can be computed from the second derivatives by taking the inverse of the induced metric times Laplace times the covariant Hessian of the position vector f. So this is the second derivatives of f xi xj minus Christoffel symbols of the induced metric g k ij times the tangent vectors xk. And this is of course true for any component, so this is a vector equation. And notice here that in this setting the Christoffel symbols involve the second derivatives of the position vector, since they involve the first derivatives of the metric. Since you have GKL is equal to df dxk times df dxl, you compute that the Christoffel symbols in this case are just given by taking the second derivatives with respect to xi, xj, and multiplying with df dxl, and then raising one index. And you can also see it, I guess, from, yeah, no, this is just a computation from here. And this means that when we now compute the symbol of the linearization, it's again quasi-linear, so it's linear in this term and it's linear in this term, so it's easy to compute the symbol at some f naught in direction of some theta. Well, we get actually, we can make this even simpler. We can express this, right? So we can write this as G upper ij times d2f dxi dxj, using this formula minus the inner product of d2f dxi dxj times df dxk times gk l times d, here's an l, and then here we get df dxk. And you see that this here is just the projection of the second derivatives of f onto the normal part, because I'm subtracting the tangential part. So this is nothing else but Gij of the d2f, the xi, the xj normal component, I guess another way of writing this would be Gij of projection normal of the second derivatives of f and therefore then when we compute the symbol in direction of some variation g of the metric, what we get is g upper ij at g of theta I, theta j times the projection of g onto the normal component. So this is theta squared times the normal projection of the variation g. So we have a situation here somehow similar in this, to Ricci flow. We have sort of in one direction of variations, as long as we have normal variations, it acts by multiplication with theta squared. So sigma dh of f0 at theta acts actually on any f0 acts on g by on the normal part of g by multiplication with theta squared. And now this normal part of g is of course the null space of that operator which projects on the tangent space. So this suggests that here the right integrability operator is exactly the projection onto the tangent space, because then on the null space of that projection we have parabolicity. Let's formulate that. So if we set J of G to be the tangential component of T, then we get that J of F0 applied to the mean curvature vector at F0 is equal to 0, because our speed vector is the normal speed, right? The mean curvature vector is pointing in normal direction, so our J acting on our actual speed is 0, which was the first condition, i.e. J is an integrability condition. And secondly, as we have just seen, on the null space, and so sigma of the linearization of H at F0 applied to theta acts on the null space of J of F0 by multiplication with zeta squared. So at this abstract level, we have exactly the same thing as in Ricci flow. We have an integrability condition of first order, and we get this condition, just like the first Bianchi identity, the second contracted Bianchi identity applied to Ricci tensor gave us 0 in the case of Ricci flow, and then on the null space of the projection, which is the tangential projection, which is the normal part. On the normal part, the symbol acts by multiplication with zeta squared. So the conditions are satisfied. So conditions of Hamilton's general theorem are satisfied. And therefore you get short-time existence. And in fact, you can use exactly the same argument to get all the other well-known short-time existence results, say for Gauss curvature flow, or for the harmonic mean curvature flow, or the two harmonic mean curvature flow. It all boils down to just check the usual calculation that the operator on the right-hand side is elliptic, and then you kill the degeneracy that comes from the diffeomorphisms, and the diffeomorphisms are, of course, exactly the tangential vector fields, because they describe the diffeomorphisms, and you get the short-term existence result. But I would like to point out also that the analogy is similarly striking when you look at the de Turck trip. So the analog of de Turck flow, well, in this case, it's very obvious, right? We have ddt of f is equal to gij d2f dxi dxj. This is the nice part, and the thing that is giving us trouble is this term gamma ijk with respect to the G metric k df dxk. So we would like to get rid of this term. So what we do, we take exactly the vector field which cancels this term and add it to the flow. So define a vector field W K, and well, you take exactly Gij times gamma k ij. And to make it a vector field, you subtract some initial data, say the connection of the Levi-Civita, connection of the initial induced metric, and you end up with this vector field, and then solve ddt f tilde is equal to gij d2 equal to the mean curvature vector, which is this, and then add on plus w. And this is, of course, a tangential vector field. Like this. Yeah, these are the components with respect to this metric, right? So this is a tangential vector field, so it only changes the mean curvature flow towards something which doesn't change the geometry of the moving hypersurfaces at all. It just changes the parameterization on the surface. And this new thing here, well, when you work it out, here you're just obviously subtracting this term, so you end up with Gij, d2f, dxi, dxj, and the only thing that you get in addition is a lower order term, Gij, times the gamma bar Kij of the background metric, which is a lower order term. And therefore the symbol of this thing is now exactly multiplication by theta squared. So the symbol of dq tilde, right hand side tilde, at f0 times some direction theta is nothing else in direction of some g, some variation g, is just theta squared times g. Therefore it's parabolic. So this can be solved. This has a solution. Solution with smooth W, then consider, then use phi of t as before, ddt phi of t equals minus W, and take f to be phi with f tilde, and to solve the original equation. And it's striking that you're getting away here with exactly the same vector field as in Ricci flow. It's not just an anomaly, it's the same vector field. You use exactly the same vector field in order to make the mean curvature flow parabolic. There's of course other ways to break the diffeomorphism invariance. You may have seen other proofs for mean curvature flow where you say, right, the flow in normal coordinates above the initial surface. And this is another way of breaking the diffeomorphism invariance along tangential directions because it leads to a single scalar parabolic equation that satisfies our very first definition for scalar equations to be parabolic. And that indicates in turn that the de Turk trick is not the only one that gives you a solution to Ricci flow. You could use other diffeomorphisms and they may be useful in other contexts. All you have to make sure is that you get a positive real part on the resulting symbol. And with that, I think we leave the result on short-time existence, and then in the next lecture we look at the long-time behavior of the flow and aim at understanding what is the criterion for the flow to stop. If it doesn't have a solution for all time, can we write down a criterion that the flow has to violate if it stops existing. And in fact, we will prove that as long as the curvature is bounded, we can extend the flow. So our criterion for a singularity, our first criterion for a singularity, will be that the curvature blows up at the singularity. But for that, we have to do some work, and that's in the next lectures.